Throughout this course, we've been writing sentences in English about sentences in logic. We've been writing informal proofs in English about formal proofs in logic. The natural question to ask is whether logic can be used to describe logic itself. Interestingly, the answer is yes. In this lesson, we're going to look at a small subset of this problem, namely the use of Herbrand logic to formalize information about propositional logic. Basic idea is this. We represent expressions in propositional logic as terms in Herbrand logic. We write Herbrand logic sentences to define basic concepts of propositional logic, and then we prove meta-theorems as formal theorems in Herbrand logic. Ultimately, we can extend this to formalizing information about Herbrand logic as well. Formalization is a bit messier, and some nasty problems need to be handled, notably the problem of paradoxes, but it can be done. And what follows, as I said, we're going to make each proposition constant in our propositional language an object constant in Herbrand logic formalization. For example, if our propositional language has relation constants p, q, and r, then we will use p, q, and r as object constants in our Herbrand logic formalization. Next, we'll introduce function constants to represent constructors of complex sentences. There's one function constant for each logical operator. NOT, not, for negations, and for conjunctions, or for disjunctions, if for implications, and IFF, if and only if, for biconditionals. Using these function constants, we can then represent propositional logic sentences as terms in our Herbrand logic language. For example, we can use the term and of PQ to represent the propositional logic sentence P and Q, and so forth. Finally, we introduce a selection of relation constants to express the types of various expressions in our propositional logic language. We use the unary relation constant proposition to assert that an expression is a proposition. We use the unary relation constant negation to assert that an expression is a negation. We use the unary relation constant conjunction to assert that an expression is a conjunction. We use the unary relation constant disjunction to assert that an expression is a disjunction. And similarly, we use implication for implications and biconditional for biconditionals. And we use the unary relation constant sentence to assert that an expression is a legal sentence. With this vocabulary, we can characterize the syntax of our language as shown here. We start with the declarations of our proposition constants. P is a proposition constant, ditto for Q and R. Next, we define the types of the expressions involved using our various logical operators. If X is a sentence, then not of X is a negation. And of XY is a conjunction if X and Y are sentences, and so forth. Finally, a sentence is either a proposition, or a negation, or a conjunction, or a disjunction, or an implication, or a biconditional. And that's all. Now, with a solid characterization of our syntax, we can formalize our rules of inference. We start by representing each rule of inference as a relation constant. For example, we use the ternary relation constant AI to represent and introduction. And we use the binary relation constant AE to represent and elimination. With this vocabulary, we can define these relations as shown here. If X and Y are sentences, then using and introduction, we can deduce their conjunction. If X and Y are sentences, then using and elimination, we can deduce X, and we can also deduce Y. And the other rules of inference can be formalized in similar fashion. Continuing in this vein, we can define proofs, both linear and structure. We can even define truth assignments, satisfaction, and the properties of validity, satisfiability, and so forth. And having done all this, we can state various meta-theorems, such as the validity of sentences, the soundness of our proof methods, and so forth. And we can use proof methods discussed in the next lessons to prove these meta-theorems formally. We can use a similar approach to formalizing Herbrand logic within Herbrand logic. However, in that case, we need to be very careful. If done incorrectly, we can write paradoxical sentences, that is, sentences that are neither true nor false. For example, a careless formalization leads to formal versions of sentences like, "This sentence is false," which is self-contradictory and therefore cannot be true and cannot be false. Fortunately, with care, it's possible to avoid such paradoxes and thereby get some useful work done.